All right, in today's lesson, we're going to look at differential equations and how they relate to slope fields. Now, we've actually talked about differential equations before, but just as a refresher, differential equations are just equations that involve rates of change, okay? And that means they're already like the derivative has already been taken. And so they can often be solved using techniques of anti-differentiation. All right, so let me show you what we've done with them before. All right, so if I ask you to solve the differential equation for the general solution, okay, and I give you the differential equation dy over dx equals, and let's say it equals negative 0.56x plus 24.9, if you were going to solve that, the first thing you have to do, you absolutely must do, okay, is separate the variables, okay? That is absolutely the first thing you must do, okay? If this were a free response question, you absolutely must show that. What do I mean? I mean anything that has an X needs to be on one side and anything that has a Y needs to be on the other. All right, so in this case, we are going to have to multiply dx from the left to the right, okay? And then you're ready to integrate. All right, so you're going to show that you're going to integrate both sides. And when you integrate dy, you get y, right? Because you're really integrating 1 with respect to y, so you get y. And on the other side, let's see, since this one has an x, we need to apply the power rule. So we're going to add a power and divide our fraction by 2. All right, so we actually, oh, I didn't give myself enough room. We actually get a little bit smaller of a decimal. All right, and then we put an x on this one. And then don't forget we're finding the general solution, so we put a plus c. Now, if you are given some other information that you could find c, okay, then you could solve for c and find the particular solution, okay? So I'm actually going to give us an example of that. So we're going to solve the differential equation, all right? And a lot of times that's all the directions say, and you have to know that that means either find the general if you don't have extra information, or find the particular solution if you do, okay? So here is my example, all right? dy over dx equals, let's say 1/5 times 100 minus y, all right? So there's my example, and I want us to solve. I also need to tell you, oh, okay, so, my bad. Okay, so I thought I was going to be asking you for a particular solution here. I didn't specify whether you needed the particular or general this time, and because I'm not giving you that extra information, then you know that you're finding a general solution. All right, so here is where you have to be, pay close attention, because 100 minus y has the variable y in it. So you need to make sure that when you separate the variables, everything that has a y goes on one side and everything that has an x goes on the other. Now, technically you could move the 1/5 with the 100 minus y, but then you'd have to divide by a fraction, and so might as well leave it where it's at, okay? And now you're ready to integrate, okay? So you do have to integrate both sides, and you're integrating the left with respect to y, and you're integrating the right with respect to x. So you do have to pay attention to little details like that. And the right is easier, and when you add c, you only add it to one side, and it is usually the x side. All right, now how do I integrate the left? So I just have to remember that it might not just be a standard power rule or constant rule or something. And so if I have something on the bottom, like 100 minus y, I may have to consider u substitution, okay? And then the derivative of that would be -1 dy which I can compensate for because I've already got the dy. And so I haven't integrated yet. I just want to show you what we've got. The bottom was u. I'm going to bring it up. Okay, and so then I have to remember I can't apply a power rule here. This is a special integral where you get the natural log of the absolute value of u, all right, and then we've already put the plus c on the other side. Okay, now if you want to drop the actual 1 that's with your negative, that is certainly fine. The 1 is understood. Okay, now in terms of finding a particular solution, like if you were working a problem like this, you would actually want to, I know we haven't solved for y here yet, and you wouldn't want to solve for y before you found c. So you would definitely want to solve for y after you find c using whatever given information that you have. Okay, now a couple of things to keep in mind with differential equations is that the solution to a differential equation must satisfy the differential equation. Okay, so let me show you what I mean by that. All right, I'm just going to give you an example. So I want to show that this solution, okay, is a solution to the differential equation dy over dx equals 0.3y, okay? So I need to show that this is a solution to that differential equation, okay? So let's start with that. If I take the derivative of it, that means I'm turning it into a differential equation. I have to remember how to take the derivative of exponential functions and follow the chain rule, okay? There's my differential equation. But supposedly, that should be the same, that should actually be equivalent to the original differential equation, 0.3y, okay? Well, what do I know? Well, since y equals e to the 0.3x, I can just rewrite this as a y right there. And so I have shown that this equation is a solution to this differential equation. So that's just something that you might be asked to do in like a multiple choice or maybe a free response. I don't know. All right, now that's just a quick review of what are differential equations and how to solve them, okay? But what we're going to do today is we're going to talk about how can you represent a differential equation graphically, okay? So we are going to see today that to represent a differential equation graphically, you can use a slope field, okay? Maybe I'll type it just to make it go a little bit faster. All right, let's say it like this. One way to represent a differential equation graphically is with a slope field. Okay, so what is a slope field? A slope field is a grid on a portion of the xy plane, like the coordinate plane, where short line segments are drawn at each point of the grid. And the slope of each line segment is determined by the differential equation. Okay, so we're going to jump over to our first packet, all right, where I've given you some grids, okay, and then what you're going to see, I'm going to show you how to draw them, all right, but then let me give you an idea, like here are some that are already drawn, and the idea is that once you have a slope field, you could actually draw in the graph of any particular solution by just picking a point and going to the left and the right and trying to stay parallel to those little line segments. And so let's write that in our notes. Once you have a slope field, you can draw the graph of any particular solution. So a slope field, it gives you a visual representation of the solutions to the slope field, and it represents a family of curves. And so once you have that slope field, you could actually draw the graph of any particular solution by picking a starting point. Sometimes you are told where to start, and you would have to go in both directions, going left and right, staying parallel to the line segments. And I'll explain all of that when we actually look at one. But main idea here, slope fields give a visual perspective of the solutions to the differential equation. Okay, and it represents a family of curves, right, or a family of solutions. Because like when you solve a differential equation, if you don't have, like if you solve it for a general solution, then you've got that plus c, and c could be anything. So that's where the whole idea of a family of solutions comes in. But once you have, once you find a particular solution, it should also fit on your slope field, okay? So we're going to jump over to our first little packet on slope fields, and I want to show you how drawing a slope field works. Okay, so we are going to draw a slope field for each of the following differential equations. Okay, and we're not going to do all 6 of these. I think we're going to do, I don't know, 3 or 4 of them together to give you an idea of how it works. I think I'm going to zoom in just a little bit. All right, so I'm going to do the first one here. And so if the differential equation, okay, is x plus 1, all right, dy over dx, remember, is the slope, like the derivative is the slope of the tangent line. So what we're going to do is that's literally what we're finding. We're finding the slope of the tangent line at each one of these points that I have given you in this grid. Okay, now you're going to assume you're counting by ones since I didn't label it any other way. All right, so like here's my origin, right? And if you look at your formula, all that matters in the formula is the x value of the ordered pair. So when x equals 0, I get 0 plus 1 is 1. So the slope of the little tiny line segment that I'm going to draw is 1. Okay, and I'm literally drawing a tiny line segment. You know what? I'm gonna try to do it this way. All right, with a slope of 1, which is about a 45-degree angle. Okay, now because x is the only variable in this particular equation, every single point that has that same x value will have the same slope, right? Whenever x is 0, the slope will be positive 1. All right, so I'm going to try to draw several. See if I can, I don't know. Nope, that's not what I want to do. I'm going to try to draw them all with the same slope of that 45-degree angle. Actually, like all of them except for my first one, so give me a second. How do you, let me see, let me delete that one and do that one again. Okay, and then we move on. Let's go to the right here. If I plug, all of them have an x value of 1, and 1 plus 1 is 2. So now I want to draw line segments that are a little bit steeper, but I don't want to get crazy, because if you think about it, every time x gets bigger, you're going to have to go a little bit steeper and steeper. So you try to make these all parallel to each other, little tiny line segments. Okay, look, that one's a little too, we want it to be slightly steeper than the last one. All right, and then when we move forward, if we have an x value of 2, we're going to get a slope of 3, so we need to be a little bit steeper. And then if I move forward one more, we have a slope of 4, so we need to get a little bit steeper. Now, obviously, we don't want to have a slope of undefined, right? We don't want to make it vertical, so we do still need to have some sort of slope, okay? Now, let's go in the other direction. If I plug in an x value of -1, -1 plus 1 is 0. So all of these are going to have a 0 slope, which means our little line segments are all going to be horizontal. Okay, and then if I plug in -2, I get a slope of -1. So now we have a 45-degree angle, but in the negative direction. I didn't do a very good job making those all parallel. Let me get rid of this one. Because you don't want your first ones to be, your ones that represent -1 to be so steep that it's really hard to represent -2 any steeper. Okay, so our next ones are going to be -2, so we're going to try to be a little bit steeper, and hopefully you get the idea. All right, and so there is our first slope field, and the idea is that you could pick a starting place, and you could basically draw in a curve, all right, that runs parallel to, you're not actually connecting the dots or anything, but you're kind of running parallel to these to get an idea of what the graph of this, I can't decide if I should go up that way, what the graph of this particular, what this solution would look like. And depending on, you know, so the idea is that all of these should look like parabolas depending on where you chose to stick it. All right, so we have this horizontal slope. That's when the derivative equals 0, you know, you've got that max or min, and so all of these should look somewhat like parabolas. Okay, and what I want you to notice is that x only, if you had x onlys, all of these were columns of parallel slopes. Okay, now in the next one, I want to give you one with only y. So that means that every single one of these points, the y value is what is going to change the slope. Okay, and then you can decide where you want to start. I chose to start that when the y value is 0, 2 times 0 gives me 0. So all my little line segments are horizontal. And then when y equals 1, 2 times 1 is 2, so I need fairly steep slope. Try to make, but not so steep I can't make it any steeper, but also not quite 45 degrees. You need to try to make them as parallel as possible. And then 2 times 2, these would be even steeper because they are 4. Again, that's another reason why you don't want to make your first ones so steep that you can't show anything steeper. All right, now when I go into the negatives and y is -1, then my slope becomes -2. Again, I'm doing my best to make little parallel segments. And then, of course, it gets steeper and becomes -4. didn't do some of these very good, but hopefully you get the idea. All right, this one's not very good. This one's not very good. So let's try those again. There we go. Okay, and you can actually see on this one that if I were to draw in a curve, I would actually have what looks like a horizontal asymptote. All right, so depending on where I was asked to draw the curve, I might have one here, all right, but I also might have to draw one down here. Okay, that wasn't a very good one. Let me, all right, maybe it would go something like this and kind of squeeze in there. There you go. Okay. So again, if your differential equation only has an x in it, you are going to have columns of parallel slopes. If it only has a y, you're going to have rows of parallel slopes. The idea of a slope field is that it represents a family of curves, so you can draw, you should be able to see some sort of shape, and the shape that you should see should represent the solution to the differential equation. That means if you actually integrated, think about it, if you integrated an x, you would go back to an x squared function, so you should see a parabola. Now, when you integrate with a y, if you were to solve that particular one, you would actually have to separate the variables, and when you integrate on the left, you get a natural log function. And so that's why you see this sort of graph. You see the natural log. If you remember, and actually that's not true. When you integrate, you get the natural log. But when you actually go to solve for y, you would get an exponential function, because that's how you get rid of logs. And depending on what c is, all right, and so yes, this does look more like an exponential function. If for some reason it was negative, then you would get these down here at the bottom, okay? All right, now I want to look at one or two that have an x and a y, and I know this video is getting long, but it is what it is. You can skip through on what you need. All right, and so for this one, we have an x and a y, which means at every single point, my slope is going to be different, okay? And so let's just start in the middle, all right, with the origin. If I add 0 and 0, I still get 0. All right, and when they're all different, if it doesn't look obvious, okay, you might want to put a little label next to it, okay? If this was a free response question and you had to like label, I don't know, 6 or 9 points, and they're not all the same, it's not obvious, I would definitely put the answer, like the actual slope, right next to it. Now, can you think of any other time where if I add the x and y, I would get 0? Okay, well, if I have a positive and a negative of the same number, I would get 0. So positive 1 and negative 1, positive 2 and negative 2, negative 1 and positive 1, negative 2, positive 2. Okay, so all of those are 0, so that's kind of nice. If I move over to where x equals 1 but y equals 0, I get a slope of positive 1, all right? And anytime that they're, you know, the x's are positive, and, you know, so like positive 2 for x and negative 1 for y, those would also be 1s. That's really steep. Let me erase that one. All right, so you can start to see some patterns here. When x is 3 and y is negative 2, I also get a slope of 1. But again, if you're not sure that the person grading it could tell, you should definitely mark them in. All right, if I go the other way, if I say that the x value is negative 1 and y is 0, I'm getting a negative 1 slope. All right, and so you can kind of see that if x is negative 2, and y is positive 1, so all of these are negative 1s. And what's interesting there is that almost looks like a straight diagonal line, just broken a little bit. And that's because it actually ends up being a slant asymptote. All right, so I'm going to pause the video and fill in the rest of this so that you can get an idea of what it looks like. All right, so I have filled in and I've kept with my pattern of having diagonal parallel slopes. So you can see that I had some diagonal positive ones, diagonal positive twos, diagonal positive threes, fours, and fives. And then the same happened with the negatives. I've got some diagonal negative ones, negative twos, negative threes, and so on. And so again, it is really good if you have the space to label each one, just so the person reading it can tell. I'm going to leave number 4 and 5 for you to do completely on your own, because that's another one with just an X or just a Y. And I do want to take a second and look at number 6. We do have a division, all right? And so you have to be careful with division. It is possible to get an undefined slope. And remember, to be a little line segment that represents that, you would be vertical, all right? And so we were going to get a vertical. Basically, we're doing miniature tangent lines. We're going to get a vertical tangent line when the X value is 0. All right, so all of these should be vertical. And I'm drawing them just slightly off to the side here, just so you can see them. Okay, and then notice that the origin does give me an undefined, whereas when the Y equals 0 other than the origin, I can get horizontal. But that origin is going to have to stay undefined. All right, and then every single other point is going to be slightly different depending on where you are. For example, if I'm at 1, 1, then I get a -1 slope. If I'm at -1, -1, and then I put a negative in front of it, I get a -1 slope. But if I'm at +1, -1, and then put another negative, I get a +1 slope and a +1 slope here. So I can start to see some patterns. I didn't draw that very well, but you hopefully get the idea. So I'm going to pause the video again and finish making my little dashes so you can get an idea of what this one looks like. All right, and then one thing I want to say, because some of these ended up being fractions, remember when your slope is a fraction smaller than 1, your line actually gets flatter, not steeper. So just keep that in mind. And you can kind of see there's some weird shapes going on here. If I were to draw something in, it almost looks like I have, it does. I have a vertical asymptote and a horizontal, because in order to run tangent to any of these, I could not cross them. All right, so depending on where I was asked to draw the solution curve, it might look that, it might be there. If I was asked to draw one over here, it might look something like that. All right, and so ideally, if we were to solve this, we would probably get probably another exponential function, just because thinking about the way this works out. Wow, we would have ln's on both sides. Okay, so that would be really interesting. All right, the next page that I'm going to have you look at is, I've actually given you some slope fields, and we're going to practice matching them with, give me a second, you're going to match them with the solution, okay? So remember, the slope field actually gives you an idea of what the solution, like you should be able to draw the solution as like the shape. Okay, so if you look at your answer choices, and this is another reason why I thought it'd be important if you were able to print this off, because I still can't fit it all on there. But like, I want to know, like, if you look down here at number 7, which one looks like I could draw in the line y equals 1, like the horizontal line y equals 1, or y equals any other constant, okay? And D is the only one that looks like I could draw horizontal lines in. Number 8, y equals x, okay? So the family would be y equals x plus any constant. All right, but where could I draw in exactly y equals x, which is a diagonal line through the origin, and that looks like it would fit nicely in H, okay? Which one looks like I could fit the parabola y equals x squared? That one kind of looks like C to me. Then we've got 1/6 x cubed. So remember what a cubic function looks like. All right, so you need to look for something that would give you that shape. That looks like F to me. Okay, 11, 1 over x squared. Right, you have to remember what that might look like. 1 over x has your curves in your opposite corners. 1 over x squared would put them both above the x-axis. And then if I shifted that up or down, that would be the plus c part. That actually looks like letter A. All right, sine and cosine are very similar. And so if you remember anything about sine and cosine, right, they look like this. They just repeat over and over. The major difference is that sine should actually go through the origin, whereas cosine does not. And so E and B look very similar, but E looks like it's going to go through the origin, whereas B looks like I actually reach my maximum when the x value is 0, which is what cosine does. And then number 14, ln of the absolute value of x, right? Well, you just have to remember what ln of x, the graph of ln of x looks like, right? It looks like this, right? And so which one could I fit that into? And that looks most like G, right? So that's really cool. I mean, that's the easiest thing I think there is to do with slope fields, is because slope fields actually shows you what the solution should look like, okay? On the next page, and I can actually make it a little bit bigger now, maybe even a little bit bigger than that. Okay, I've given you a slope field again, but this time you're matching it to its differential equation. So when you're matching it to its differential equation, you really should match up slopes, okay? You really should match up slopes, because dy over dx is a slope, right? And then remember some of the key things that we looked at. If you have just x, right, x only, you should have columns of parallel slopes, So I'm thinking it's B, but I should check some points, all right? And I noticed that all of these are horizontal, and all of these have an x value of 2, all right? No, excuse me, all of these have an x value of -2. And if I plug in -2, would I get a 0 when I work it out? And I would. And then I can just check a couple other points. If I plug in a -1, I would actually get a slope of +1/2. If I plug in a 0, I get a slope of +1. So B is looking really good for this. All right. Then remember, we talked about ones that only had y's should have rows of parallel slopes. All right, so D looks really good for that. Just double check. When y equals 0, I'm on the x-axis, and it looks like I don't have any, I mean, you can't really see them, but they are there. They're all flat, okay? And then if y equals 1, these should all be a slope of 1, and so on. So that one looks really good. All right, but then when you have the 2 letters, it's really important that you check some different points, okay? So look at A. It looks kind of like a circle. It looks like it makes a circle. And I noticed that whenever the x value is 0, I get 0. It also looks like whenever the y value is 0, I get 0, okay? So when they're both 0, it looks like I'm going to be getting zeros. And let's see, so when I divide, now I can't really tell what's going on with the origin. And that's the only time when they're both 0 at the same time. But what I'm saying is when x is 0, I get 0 every single time. Interesting. And then, you know what? I don't think anything is actually marked there. I don't think anything is technically marked there. But if you're not sure, you know, like check some other points. So if I go over to, I don't know, 1, 1, okay? If they're both positive and I subtract them, will I, both positive ones, 1 minus 1, will I get a slope of -1? No, I won't. Okay, so that right away eliminates 17, and 18 was looking better anyways. but you just need to take some time and check slopes. So when you're matching slope fields to their differential equations, check slopes. All right, so 17 ends up matching C the best, and 18 ends up matching A the best. Okay, now what else might you be asked to do with slope fields? All right, well, here is a slope field that's already given to you. All right, and it says the solution curve passing through the point 0, 1 is already shown, and it wants you to sketch a solution curve through the point 0, 2. So here's 0, 2, and since it represents a family of curves, I should be able to draw a parabola right inside there. All right, sketch a solution curve through the point 0, negative 1. Well, you can see that when I move down to the negative 1, that it looks like all of my slopes turn the other way. So more than likely, right, I'm not connecting the dots, but I'm like kind of following the dashes, trying to stay parallel to them. I should get a downward parabola. All right, number 20 is giving you another one where we have x plus y, and it wants you to sketch 2 more solution curves. All right, so if I go to the point 0, 1, I want to sketch a solution curve through that, and I have to follow the curves. So the whole idea is that you can see that these are getting steeper, all right? And then, but when you come back here, it actually flattens out, and then it almost looks like we've got this diagonal tangent line, or excuse me, diagonal asymptote. I probably got too close, but you get the idea there, hopefully. You're just running along the slopes. Let me zoom in, because that might make it easier for me to actually draw. Okay, and yeah, all right. And then another one says negative 3, 0, so you got to make sure you go through the right point. And then, okay, so whoop. All right, so it almost looks like this is like a tangent line, an asymptote that we can't really cross. And the slopes, again, we're not really playing connect the dots, but you're just kind of trying to stay and go in the same direction as your little slopes. Okay, all right, that finishes off this packet. I have another packet where you're going to match up some slope fields again, lots of matching, and then the last page actually has you practicing some AP type questions, and so that's where you really need to spend some time again practicing like what you might be asked to do. You're going to be solving some differential equations, and if we have time in class, I'll certainly go over that, but this video is more than long enough.